So the next talk is given by Delphine, that is a professor at the University of Lund. She's working on building acoustics since more than 10 years. And she's also working in the area of research with students and so on. So it gives her a lot, and we're jealous, because it gives her a lot of capacity in working in this subject. Because she has slaves working for her.
I'm living in Sweden. Slavery is not allowed.
Oh.
We have to pay them just to make it.
Students.
Yes, exactly. So now I will talk about, I will say, the topic of the Silent Timber Build project that is perhaps a little bit more headache oriented. We will talk about calculation methods for wooden construction. I will try to give you an overview, and I will share this presentation with my colleague from the CSTB, Guigou. So it will be one presentation. We will not stop in the middle. We just change the intervenants. We were thinking it would be more smooth like that. So I just have to know how it works. Yeah. So when we talk about acoustic issues in tall wooden building, we usually talk about, of course, acoustics. But as we have seen during the previous presentation, what we call the low frequencies problem is or are the predominant issues nowadays. People are complaining about impact sound. I will explain a little bit after what is impact sound and how we measure it. But it's all this boom, boom when you walk, when you are able to listen, even if you don't want your neighbors playing Minecraft or other games. You have all the frequency going in your living room. You really don't appreciate it, and so on. Or when you hear the neighbor's door smashing, all these type of problems. So we have tried in the frame of a Silent Timber Build to break down the frequency range. So we start at 5 Hertz. Here, that we call vibration. After, it's a question of definition, whatever. So here we decided we start vibration. We have usually the tools that we're using for this type of frequency range are finite element method. I put FEM, but it's cover all type of finite element. And after that, we are going a little bit upper in frequencies. Let's say approximately 150 Hertz and a bit more. It's when it starts to be a little bit difficult to extract what is vibration, or what do we perceive as vibration, or what we perceive are acoustics waves. We are not really sure. So instead of have philosophical discussion about that, we decided to work these two together to see if we can have a better prediction. And for this, finite element have its limitation in more after 200 Hertz, especially for wood, because of the propagation. It's autotropic materials. So we try to add a more classical acoustic approach. That is the statistic energy analysis. And we can go in frequencies. And it's what usually we use for what we call the real acoustics, what you can really, really hear. So using this type of frequency range, we have tried to see how we can develop prediction tools for building elements, for wall, for floor. As we have seen before, the main issue is floor, okay? It's impact noise for wooden construction. For airborne noise, wall, I would say we are quite okay. I still need some little bit work on it, but it's, I would say, the safest part of the wooden construction. And the interesting and the next step will be how to model the full building. Because it's one thing to have what's happened in your floor element or in your wall, but what's happened when you have 18 story? What will be the overall behavior in terms of acoustics and vibration? Because going up in story, meaning that you have wind exposure problem. Did the wind induce noise? That is a big question. Okay, perhaps not in some part of the Europe country, but in the Nordic, I promise, we have a lot of wind. So we need to know that. And that was part of the investigation. So first, I mean, you have heard a lot about airborne sound transmission and things like that. But first of all, how we do it, how we measure it, you know, as an acoustician. Because I'm pretty sure in this room, not everybody understands or know what it is. So usually when we talk about sound transmission, you have two types. You have the airborne, meaning it's this one. When you have someone or your neighbors watching his TV, and what you can hear in your flat. That is the transmission going between the wall. And of course, you have this famous flanking transmission. And what we call flanking is a transmission going through the structure, more or less. And you have the impact transmission or the structure-borne transmission. Both words are used. It's what you can hear when people are walking, jumping, or whatever they're doing. Sometimes you wonder. And also, in addition, with the flanking transmission through the structure, but it's going down to your flat. It's when you hear your neighbors. So that is more or less what we call. The current ISO standard, at least for Sweden, we start at 50 Hertz. And the current regulation for the rest of Europe start from 100 Hertz, as my colleague said. But in Sweden, we start at 50 Hertz. So it's a little bit, I mean, it's some political discussion around that. But what we have seen for the different presentation from before, from previous research projects, not only in Sweden, but also in France, with this famous project called acoustique, I'm right, is that it's quite important to take into account the low frequencies. So in Sweden, we have pushed, is there a problem? We have pushed a little bit far. We have made some previous studies saying that perhaps we should start at 20 Hertz for the impact noise. We are discussing that, so no stress about that. I just mentioned it, but don't start to sweat. Okay, 50 Hertz, good enough. If we can make good floor solution that works at 50 Hertz, we are all safe. And as I said, for the airborne, it's not a big problem. And the main objective of this study is to try to have better prediction tools. So regarding the tapping machine, because we will, at least in my talk, I will focus more on the impact noise. And when we do, you have seen these nice curves about impact noise. But how we measure it, that is what we call, our hammer, or the tapping machine. It's a small device that you bring on the side, and it has several hammers that fall, and it's doing a lot of noise. And it should be able to repeat a human walking perception. So it's how we do. So we bring our machine, and we measure in the lower flat under the sound pressure level that it's propagating. And we applied a quite simple formula that I will not make a lecture about it, but just to give you an idea. So the main aim and the objective of the work package that I was leading was really to make prediction tools. And as you can see on these pictures, my goal is the full building. That is what I would like to do. To be able to say that, for example, in this flat, because of the bearing structure, because of where we have the escalator or the trap staircase, why in these flats the sound pressure level will be slightly different than in other, because that is a fact. It's not something that you think it will happen. It has been shown. When you do a measurement in a full building in wood, you will notice that there is differences between flats, and it's due to the structure itself. So we need to be able to do the full building. So for the low frequencies, no choice, finite element. So we go for it. And we have a specific aim, as I said, for the impact noise. Because it's very important for dwellings, but also for, I would say, offices, schools, or other buildings. But when we want to model the impact sound, we have a problem. The first problem that we have is how to model this machine, this impact noise, because we want to be able to correlate our prediction tool to the standards, acoustic standard that we have to use. So how we do that? We have three what we call unknown. The first one is the excitation source itself, how to characterize that. After is the vibration transmission through the structure. In this case, we need an accurate prediction. And how to calibrate our models. Because it's nice to do models, but using finite element, we have to calibrate them to make sure that we are using the right model, the right material property, and so on. So we have to calibrate our model all the time. And the last big problem that we have is how to predict the sound pressure field in the room below using finite element. So, and for this, we need to have, of course, the sound pressure level, but also how the room effect affects the measurements. So that almost what we are focusing on the silent tube building. It's mainly the vibration transmission. And that is a case that we have done using these volume elements. We had the chance to have access to few buildings using this technology. So we're using this. So we have done measurements and some type of mock-up that were the real volume element using the tapping machine. And after that, we have made some calibration from these measurements for our finite element model. And we have developed a calculation, not with a calculation method for that. And we see that we can have a slight overlap for the calibration. That is quite good in terms of prediction. And in this case, we have a method that have a better correlation with the human perception, going down to 10 Hertz, because at the end, it's the comfort of people that we are aiming for. So how we do to develop these prediction tools? We are using this flowchart. It's quite straightforward, I would say. We have the primary, design, structural design. So the structural designer is coming to us. We discuss. We put this in our finite elements. After we check the boundary condition, materials, and whatever. We check the performances. If it's not okay, we wonder why. What are the structural modifications that we can do? Or perhaps it's just what the people perceive. And we turn again and again until we are okay. And we said, final design, okay, go ahead. So, but one thing that when we deal with acoustics, building acoustics, that we have the tendency sometimes to forget is that everything is dependent of the structural dynamic of the buildings, of the materials. So we have to take this into account. So that is one thing that we add. So we are using this 4-step to set up the finite element model. After we calibrate it using model tests and so on, energy mapping, synthesis, different method. I will go fast because time is running. After that, when the calibration, we agree with it, we go for the optimization of the model, making calculation faster. And after we improve, if we think it's needed. So it's how we do. I will just give you a fast example. I had the chance to discuss with Michael Green about his big building in Prince George, this innovation center. And I have tried to make a design and to test the method that we have developed regarding wind exposure for this type of buildings. So we have pushed the model. We are taking his structure, his modeling. We have pushed up to 32 story, because that is something that he was talking many years ago about it. So what we did is that we have done a model of 1 story, and after we have done the model, put everybody together, each model together, we have made, of course, some reduction model and blah, blah, blah. And we got the first deformation, is the one that you have. That is the 4th mode, when you have a wind exposure here. And it's approximately 1 Hertz. And that are the results from different floor. Here you see that you have floor 20, floor 32, and so on. And actually what we were able, and we compare it with the ISO regarding audible threshold curves, how much you perceive the wind. And actually the main conclusion of this modeling was that actually it was okay. We can do it. So it's not, depending on the structure, it could be possible. I don't know how much I have left, Jean-Luc?
4 minutes.
4 minutes. So, 3, okay. So regarding the, to be back in, finished. Okay, regarding the tapping machine, 2 minutes. Okay, I will go. But one thing that is, I would like really to talk about the tapping machine is that we have made an investigation to see how to model the tapping machine. Because usually we are using more the time domain than the frequency domain. And the question that we're trying to see is that, are they equal? Because if you're working in the frequency domain, you win a lot of calculation time. And the answer was that it was better to do that. So the conclusion, and after I will let the floor to my colleague, it's that the frequency calculations are much faster for when you want to model. And you can also increase accurately when the model, when you want to compare two measurements. You can apply this method to other type of excitation, as the wind, for example, or something like that. As soon as the excitation time is known, of course. And usually the time domain method, usually you have to include numerical damping time to reach the steady state and so on, are avoided in this case. So we try to make a shortcut. So we don't win only on the calculation time, but also in the implementation time. So much better. So we will still work on how to make the contact between this armrest and the floor, the uncertainty evaluation. And that it's what we should do. So, and now I will finish with the low frequency part, and I will let the floor to my colleagues that will talk about the higher frequencies. Cathy, please.
So Catherine Guigou is a research scientist from CSTB, that is a technical center for construction, or Technical and Scientific Center for Construction in France.
Thank you, Jean-Luc.
Welcome.
So in this part of the talk, we will try to concentrate on the mid to high frequency range. And for this case, we use a different type of modeling, which is called statistical energy modeling, in that sense that we only look at the energy that propagates into the structure or from one subsystem to another subsystem. It can actually deal with both the airborne and the structure-borne path that can be included in these two models. So in the project Silent Tiber Build, we worked with the software Seawood that was provided by our partner Interact, who's not here today, but we thanks him to be able to use that software. And so we can, this is an example of a wall. We have to describe it into subsystem, each boards, the studs, the different elements that connect the two boards, and then the emission room as well as the receiving room. This is just an example of how you have to describe your system. So this was some calculation that was performed by Jean-Luc, I think. Gérard. Okay. So this is just a simple double frame separating wall with some mineral wool in the middle, and you can see that the statistical energy model is able to match very well the measurement data, even started at 100 Hertz, because in that case, the modal behavior of the wall is not very important. Okay? But if we go lower than 100 Hertz, then that would be becoming more complicated. We also had a tool that was able to connect the finite element modeling of a system to the SEA modeling through the inverse method. So this requires a lot of different calculation. You have to extract all the different modes from the finite element models to calculate some transfer function between different nodes on the different parts of the substructures, etc. It's still quite complicated, I would say. So in most of the project, I think we looked at the FEM modeling and then the SEA modeling. It was really, I mean, it's quite complicated to have one single software that does everything together right now. It's there, but still very complicated to use, okay? These are just some other measurements to show you how the airborne path through a double wall, to a double frame wall is affected by some structure-borne effect. So, oops, I'm sorry. So you can see in the upper part, we only predict what's going through the cavity of the double wall. It's a double frame, so there is no structural connection between the boards through the cavity. And you can see the prediction in blue here and the measurements in red. And we were wondering why our prediction was so much better than actually what we'd measured. That was measured at FCBA, okay? Not at CSTB, okay. And actually we found out that there was some structural path between the external walls of the double wall through actually the laboratory walls, ceilings, and floor, okay? And actually when we took this into account in the SEA model, we were able to actually match the measurements, okay? So we have to be really careful when we do measurements in the laboratory and make sure that we avoid all these flanking paths. Okay. In order to look at impact sound, at CSTB we developed a little model in parallel with this other Seawood approach. And we decided to use our software that we use as a standard thing, which is based on the wave and transfer matrix theory. And we actually modeled the structural path to the SEA model. And the different boards are connected by point connections. And we looked into the impact sound for different joist floors. Concerning the excitation of the impact machine, which is quite difficult actually to model, we use what we had in the ACOUSTIQUES software, which is already implemented. We just modified it in terms to have access to the impact force as well as the structural mobility to take into account and calculate actually the power injected in the system. Of course, when we're going to look at the results in the low frequency range, there will be no match with this theoretical prediction because we know that we need the finite element modeling. Okay, so this is a first example, which is the standard reference flow in the ISO 10140 Part 5 standard, which is a reference flow that nobody uses in reality. Okay. It's not even available at the laboratories, I think. But anyway, we started with this since it's a reference flow. And we had one measurement at CSTB and we had one measurement at IBP that were done a few years back when the standard got out, I think. So anyway, and so we did some prediction. You have the description of the system right here. You can see first between the two measurements at the IBP, it's in Germany, and CSTB in France, you already have some differences. Some actually large differences in the low frequency range. Okay. Well, the laboratories are different, the mounting is different, the boards are slightly different, etc. The screwing might be slightly different, even though it's really well described in the standard. Okay. And then you have the prediction method, where we use like really stiff connections between the top and the lower boards in terms of connections. And you can see it's not perfect, but it's fairly good. It could be another measurement from another laboratory, you wouldn't know, okay? Except like in the low frequency range, like I said, this method is not appropriate, okay? So in terms of global index, if we look at the LNW, we're pretty much in the right range. Same thing for LNW plus C. Then when we had the low frequency range, of course, it's not good because the model is not valid. Okay. Another system that I will show here, it's a little bit more complicated because we have a floating system on top of the joist floor. and we have some resilient elements to suspend the ceiling. Okay? Fairly good. You have some accidents in the curve that are not completely matching what we have in terms of the measurements. I mean, here and there, but globally, the slope is fairly good. Again, the low frequency range is not appropriate. Here you have some critical frequency of the different boards, mostly the ceilings, and here you have some resonance effect regarding to the suspensions. In terms of global index, again, it's not perfect, but it's good enough to have a prediction, optimize, and go to a next step. Okay? Now we'll talk more about the prediction for the complete buildings in terms of energy analysis. And like Jean-Luc mentioned, we had discussed action. That's a little bit dating, 2008. It's a long time ago, isn't it? Well, anyway, so we worked a lot on the SEA-based approach for the complete buildings, trying to evaluate the flanking path from 50 to 5 kilohertz. I think this discussed action was quite successful, and actually we were able to put a lot of results of discussed action into the new EN 12354 version of the standard, and in order to fit the specific of the lightweight wood frame buildings. Concerning the CLTs, the models we have today is pretty much good. We don't have to change the approach. We can pretty much use what is already available in the standard, except that we don't have data for the junctions. Okay? So in the new version of the standard, we propose some new data for the KIJ for the junctions to be able to calculate the flanking path. Okay? But if not, the standard approach, it's correct. Okay, this new version of the standard, which will be actually an international standard, it will be an ISO standard, should be published in the fall. I thought it was September, but it's not out yet, but it should be coming shortly. So you have, we deal with part 1, which is related to the airborne sound insulation between rooms, and we did with part 2, which deals with the impact sound insulation between rooms. Mostly, okay, I will jump the, huh? Okay. What is quite important, actually, is the junctions. We had to renew the definition to describe the junction and the flanking path for the lightweight frame elements. So this is the expression. You don't have to remember anything, but I think we cannot use what we call the KIG, which is the standard for homogeneous or even CLT elements. Here we have to use the DVIJ, which is very similar, but it's got a different name. It's more to complicate people's life, I think, but anyway. And then we had to look for empirical data for the junctions. So through the ACOUSTIQUES project, we did a lot of measurements on different junctions. And also in Germany, they did a lot of measurements on junction. In Italy, in the different countries, they made a lot of different measurements. And so we compiled everything, even though the systems were very different, because you can see, like, for joist element, I mean, you have like tons of different junctions. And so we kind of regrouped junctions into categories. We did the same thing for CLT junctions to try to figure out some kind of empirical data that you can use for the model. Even your junction is not exactly the same. Okay? It's a first approach, and then when we gather more and more data, then we can increase the precision of the prediction. Just to give you an example of some junction measurements that we carried out through the ACOUSTIQUES project, we did some measurements in two different buildings that were exactly the same ones in terms of designs. Okay? And of course, we obtained different results. Well, it's not funny, but you know, the walls, I mean, the walls and the floors were industrialized, so they were pretty much the same floors and walls, okay? But then the connection, when you put them on the site and connect everything, of course you have a little bit of differences. And when you measure the junctions, you can see, for example, here you have like, I don't know, 8 dB difference. That could have an effect on the flanking path, especially in the high frequency. Okay? For some junction, it was fairly close, and for some other ones, you have. So workmanship is one main point that we have to be careful about, and talking to the people in the field, the way they build, and maybe teach a little bit more what is important, what they have to be careful about when they actually put everything together is, I think, quite important. Just some examples of the junctions that you will find in the standard. We did group junction, and we decided to put together whatever the direction of the joist with the wall, the same value, just to simplify everything as a first step. Okay? No, I'm from CSTB, Catherine Guigou, I have 5 more minutes if I want. Okay, same thing for junction for CLT. We ended up with values, and you will see some of the values depend on frequencies. For homogeneous junction, most of the time you don't have a frequency variation of the junction description in terms of KIG, but here it really depends on the frequency. So you have really to take this into account. Just something else, we did a lot of measurements of junctions, but we can also make finite element modeling of junctions. So since we look only at the vibrational fields, it's easier to go higher in frequencies. So here we can go up to a couple of kilohertz, actually, to calculate the junctions. And this is just an example of a junction we did calculate. The measurements is in red, and we did some variational of the property of the components, and you can see it's fairly included in the variation of the elements, but the variation is very large. It's 15, 20 dB. Okay. We did try to evaluate the prediction method that will be in the new standard compared to the measurements we performed in the French acoustique project. And you have here some example of the differences that you have between the predicted and the measure values. I mean, it's not small, it's not large, it's pretty much like concrete buildings, okay? So it's a first step. I think we can refine the method after we gather more and more information for the different measurements in the different countries. But I think as a first step, we're in the right direction. In conclusion, 1 minute. So we have prediction method for evaluating the acoustic performance of wood-based building, but also wood-based walls and floors. And now I think we can cover the frequency range from 50 to 5 kilohertz. So it's a big step. One major problem, and it's the components variability that are not acoustically evaluated in the laboratories. Okay, so we need to think about more measurements, maybe, or more different models to take into account this variability to be able to know what is the difference we're going to have between different walls that are going to be constructed, supposedly with the same components, but not exactly the same components. Okay. So I think with silent timber build, we did answer some questions to major problems. Of course, we could go on forever, but I think it's already a big step that we went through. We can calculate and optimize the components regarding the acoustic performance. And we also calculate and optimize the buildings regarding to the acoustic performance. Thank you.